Delta-delta connections are represented by two delta phasor diagrams. In this example, the phasor diagram illustrates the primary connections, and this phasor diagram represents the secondary connections. The uppercase letters A, B, and C on the primary phasor diagram illustrate connections to the primary phase wires of a delta system. The lowercase letters A, B, and C on the secondary phasor diagram illustrate the connections to the corresponding secondary distribution lines. We'll again use this simplified diagram of three-phase transformer bank to demonstrate how this connection is made. To make our explanation easier to follow, we've numbered the transformers and their windings 1 through 3 as before. The primary windings in this transformer bank have already been connected in a delta configuration according to the primary phasor diagram. To finish the delta-delta connection, the secondary windings must be connected in a similar relationship according to the secondary phasor diagram. Again, to simplify our explanation, we've numbered the sides of the phasor diagrams that correspond to the windings in the transformers 1, 2, and 3. We'll begin the secondary delta connection with winding number 1. On the phasor diagram, this end of the winding is connected to the X1 bushing, and this end is connected to the X3 bushing. For the moment, we'll leave the X1 end of the secondary winding and move on to the X3 end of winding number 1. According to the phasor diagram, the end of secondary winding number 1 is connected to the end of secondary winding number 2. On the transformer bank, this connection is made by installing a jumper between the X3 bushing of transformer number 1 and the X1 bushing of transformer number 2. The phasor diagram shows us that the other end of winding number 2 is connected to one end of winding number 3. On the transformer bank, this connection is made by installing a jumper between the X3 bushing of transformer number 2 and the X1 bushing of transformer number 3. To complete the secondary delta connection, the other end of winding number 3 is connected to the end of winding number 1. In our example, this connection is made by installing a jumper between the X3 bushing of transformer number 3 and the X1 bushing of transformer number 1. When all of the connections are made, each end of a secondary winding is connected to the ends of the other secondary windings. In this example, notice that the phasor diagrams are in identical positions. That is, the uppercase letters of the primary phasor diagram, which represent connections to the phases of the primary system, correspond to the position of the lowercase letters on the secondary phasor diagram, which represent connections to the secondary distribution lines. Notice also that in making the connections, we've established a relationship with the ends of the primary windings and the ends of secondary windings. That is, the H1 end of each primary winding is the same relevant position on the primary phasor diagram as the X1 end of each secondary winding on the secondary phasor diagram. In simple terms, this means that power supplied to the H1 end of a primary winding is in a similar relationship to power supplied by the X1 end of the secondary winding. To illustrate this relationship, in this example, we'll designate the three-phase wires of the primary distribution system as Phase A, Phase B, and Phase C. These correspond to the uppercase letters on the primary phasor diagram. We'll also add three secondary distribution lines to the illustration. We'll designate these lines lowercase a, b, and c, which correspond to the connections to the secondary distribution lines on the secondary phasor diagram. To establish the relationship between the H1 and X1 ends of the primary and secondary windings, whatever phase that the H1 end is connected to should correspond to the designated secondary line that the X1 bushing is connected to. On transformer number 1, the H1 end of the primary winding is connected to A phase. Therefore, the connection between the X1 bushing of transformer number 1 and the X3 bushing of transformer number 3 is connected to secondary line A. On transformer number 2, the H1 bushing is connected to phase B. Therefore, the connection between the X1 bushing of transformer number 2, the X3 bushing of transformer number 1 is connected to secondary line B. The same relationship is maintained for transformer number 3. The H1 bushing is connected to phase C, so the connection between the X1 bushing of transformer number 3 and the X3 bushing of transformer number 2 is connected to secondary line C. When these connections are made, each secondary line is being energized by separate ends of two secondary windings. Secondary line A, for example, is energized by the X1 side of secondary winding number 1 and the X3 side of secondary winding number 3. Similar relationships exist for the other secondary lines. Because of the relationship we have established between the H1 end of the primary winding and the X1 end of the secondary winding in each transformer, this delta-delta connection is said to have 0 degrees of angular displacement. That is, there is no phase shift between the power supplied by the primary windings and the power supplied by the secondary windings of the three-phase bank. We can see this relationship better if we refer to the phasor diagrams. In this arrangement, there is a direct correspondence in both the position and the designation of the primary phases and the secondary lines. The H1 end of primary winding number 1 corresponds to the X1 end of secondary winding number 1. In other words, there is 0 degrees of angular displacement between the windings. The same relationship holds true for each winding in the bank. There are many ways of making a delta-delta connection. If we were to rotate the secondary phasor diagram 180 degrees, for example, we would change the angular displacement. The delta-delta connection, according to this arrangement, would produce 180 degrees of angular displacement between the primary and secondary windings. You'll notice that no connection has been made to any of the X2 bushings in this bank. This means that in this example, each secondary line is being supplied with the full rated voltage of each secondary winding. The rated output of each of these units is 240 volts. Therefore, connections between any two of the secondary lines will supply 240 volts to a secondary load. This is sometimes referred to as a straight power bank. Its primary use is for industrial and commercial customers with large three-phase power requirements. On our illustration, we'll add a grounded neutral and connect the X2 bushing of transformer number 1 to the grounded neutral. In this arrangement, when the bank is energized, connections between any two of the secondary lines will provide 240 volts to a secondary load. At the same time, connections between secondary line B and neutral, or between the neutral and secondary line C, will provide 120 volts. However, a connection between secondary line A and neutral provides 208 volts is called a power leg. This is called a power leg or a wild leg. Splitting the secondary winding on transformer number 1 effectively eliminates half of a winding on the delta connection between transformers number 1 and number 3 and produces the 208 volt power leg. Although not as efficient as a straight power bank, this type of connection allows you to provide single-phase and three-phase power from the same bank. This is what a delta-delta connection looks like in the field. We can tell it's a delta-delta connection because each primary winding is supplied with power from two separate phases of the primary system. Likewise, each secondary line is supplied from two different secondary windings. In this example, leads from each bushing are brought down from the spool rack of the secondary bus, and a delta connection is made at the spool rack. Here's the grounded neutral wire with the lead from the X2 bushing of transformer number 1 connected. This tells us that 120/240 volts can be provided from this bank. The connections at each of the remaining spools are the delta connections to the secondary lines. Here's A, here's B, and here's C. The voltage between any two of the secondary lines is 240 volts. The voltage between line A and neutral and line B and neutral is 120 volts. The voltage between line C and neutral, the power leg, is 208 volts. In this example, we used additive polarity transformers to build this three-phase bank.